All right, good afternoon, everybody. Let's get started. Sorry for the technical difficulties, but we'll be with slides set up in just a minute. But in the meantime, we can get started. My name is Silvina Hanono-Walkman. Looking forward to working with all of you this semester. And before we actually get into the topic of today's lecture, which is combinational devices in Boolean algebra, I just wanted to have you guys all turn to the second slide for a second so that you become familiar a little bit with our 6004 website. So if you haven't noticed yet, we use 6004.mit.edu as our website, not Stellar. And so here we go. So the top tab looks just like this. And you can basically go to find anything about our course from here. Specifically, I've highlighted a couple of the important tabs. So the home page is where you can find class announcements, as well as the contact information for all of the staff. All of the course information regarding grading policies and everything you need to know is in the course information tab. The handouts for the lectures and the videos, recordings, and all of that are under the resources tab. And then the lab handouts is the only thing that won't be under the resources tab. It'll be under the labs tab. And you hopefully have already signed up for Piazza for this class. If you haven't, then we strongly recommend that you do. That's our best way of communicating with all of you. And finally, the last thing is that there is this tab which will have your username, and that's where you'll be able to go to find your grades once there are grades available. Any questions about that before we move on? Yes? So what are builds? Sorry, so builds are when you actually start writing your labs. You're going to have to compile and build the BlueSpec harder description language programs that you write. And so you're going to be able to go to the build tab in order to see the status of your builds, whether or not they've succeeded, as well as the automated tests and whether or not they have passed. Okay? Any other questions? Okay, terrific. So just to remind ourselves of where we left off last time, we talked about the digital abstraction and what does it take to have a valid input and a valid output. And we said that in order to be able to handle noise, we need to be more conservative on what we consider a valid output versus what we consider a valid input. And so for our valid outputs, we have a much smaller range, which is for example, a low value would be anything that's less than VOL, whereas a valid input would be anything that's less than VIL. So what this allows us to do is that as long as our digital devices are producing valid outputs, there's room for a little bit of noise between the output that was produced and when the output is used as an input to the next device, so that the input will still be a valid digital input when it's used as we expand and connect one device to another. Okay, so today we're going to move on to combinational devices. So what are combinational devices? Well, it's basically taking this basic device that we talked about and having first of all, one or more digital inputs, which will follow the specification of the digital abstraction that we learned about last time. Did you have a question? Oh, sorry. You can have one or more outputs. For each of our devices, we're going to have a functional specification, which is going to tell us exactly what it is that this circuit needs to do. And so for this example right here, for example, it says we're going to output a 1 if at least 2 of our 3 inputs are 1, and otherwise we output a 0. So what is this circuit doing? Anybody? It's basically determining the majority between the 3 inputs, okay? And so that's our functional specification for this particular combinational device. And the last piece of information that we need is information about the timing. So we need to know what is the worst case scenario of how long it's going to take from when we have valid inputs until our output is stable and valid. Okay, so we call this the propagation delay, or the upper bound on our combinational device. And together, these four things are what we call the static discipline. So all combinational devices, in order to be valid digital combinational devices, they need to satisfy the static discipline. All right, so now we want to move on and be able to create more complicated circuits. So we want to be able to take our simple, basic combinational devices and compose them into larger ones. In order to do that, what we have to do is we have to make sure that, first of all, each of our sub-elements is itself a digital device. We then have to make sure that when we connect these pieces together, any input can only be driven by exactly one source. Okay, so either it's driven by the output of another digital device, or it's driven by a constant 0 or 1 value. And finally, our circuits, when we compose them, cannot have any cycles in order for them to be valid combinational devices. So let's take a look at this example here, where we're told that A, B, and C are valid digital circuits, and we want to compose them in the manner shown here. So to answer, the first few questions, which we want to make sure are always true, let's first review. Do we have any cycles in the way that we combine these circuits? No. Good. Is every single input driven by exactly one source? Yes, right? So for example, if you look at your C input, it's only driven, this particular C input is only driven by the output of B, okay? And similarly, because we know that the input components were digital devices themselves, we also know that the inputs and outputs are going to be valid in the system. So specifically, we're going to go through now the four pieces of the static discipline and make sure that this larger combinational circuit actually satisfies all of them. So the first thing we want to know is, do we have valid digital inputs? So because we know that A, B, and C are in themselves valid digital components, we also know that the inputs to this larger ABC module is going to have valid inputs as well. Similarly, for our outputs, we're going to have a valid output because we know that that module C produces a valid digital output. Okay, so far so good. Now what about our functional specification? How would I go about describing what this complex circuit needs to do? Can I do that based on the knowledge of what A, B, and C themselves do? Yes, right? So I know that essentially what's going to happen is if I have inputs X, Y, and Z, then I can describe what my output W is going to look like as it's going to do whatever module C does with its two inputs, where the two inputs are basically the output of module A running on inputs X and Y, and then the output of module B running on the output of A and the last input Z. Okay, is that clear to everybody? Great. So then the last thing we need for our static discipline is to be able to derive a propagation delay for this circuit. So how would I go about doing that based on the propagation delays of A, B, and C? Yep. Exactly. We're trying to come up with an upper bound, and so it's the longest path through this circuit. So if I add up the propagation delay of A plus the propagation delay of B plus the propagation delay of C, I have now generated the propagation delay for this more complex combinational circuit. Okay? And so in fact, this is a valid combinational circuit, and we can specify everything that we need to know about it. Yes?
Do all elements have the same propagation delay?
No. So you will be given the propagation delay associated with each element, and in fact, we'll see some examples of that in today's lecture. Any other questions? Yes?
If in the process of going through, your output sort of fluctuates, but it's not its final value, how would you know if it's done or if it's just some way partway through?
So you always make sure to weight the propagation delay. So you're guaranteed that if you've weighted the propagation delay, even though it's true that your output may fluctuate and go up and down a couple times before that, that's okay because you're never going to look at it until after the propagation delay has elapsed. Okay? Yes?
The whole device also needs to have only one output.
No, it can have multiple outputs. Doesn't have to. In this particular example, it has one output. Okay? Any other questions? Yes?
You mentioned an input to the combinational device. I'm just wondering what the significance of 2 arrows as inputs here is.
So this just means that, for example, module C has 2 inputs. What I was trying to say is that a particular input, which is just this one input location into C, cannot be driven by 2 things. So in other words, I couldn't have the output of B and the output of A connected to the same spot right here. That's what would not be possible because they might be conflicting with each other. Okay? All right, let's continue. All right, so let's take a little bit of a closer look at how we want to go about giving the functional specification of what it is that our circuits do. So far, we gave an example of how we just do it in English. Here's, another module, and in this particular case, it says if C is 0, then you want to copy A to Y, otherwise you want to copy B to Y. And while, yes, in this particular case, just explaining it in English, we can understand exactly what it is this module wants to do, we want to be able to have a more precise way of expressing what the functionality is. And so we have 2 systematic approaches. The first is truth tables. So the way truth tables work is you basically enumerate every single possible combination of inputs, and you specify what the output value is going to be for that combination of inputs. So if I have this module right here with 3 inputs, A, B, and C, how many possible input combinations do I have? 8, right? I have 2 to the power 3, which gives me 8 input combinations. And for each one of those, I'm going to specify what my output is going to be. And so what we said is that for the top 4, when C is equal to 0, I'm expecting it to be equal to A. And then when C is equal to 1, I'm expecting it to be equal to B. Okay? And so through this truth table, I've specified exactly what my output needs to be for every single possible input combination. All right? Another methodology that we can use are Boolean expressions. And so this is just an alternative way of expressing the same thing that truth tables do. And the way these work is as follows. We have variables that can take on one of 2 values, either a 0 or a 1. And we combine these values using 3 basic operators, which are and, or, and not. And the notation that we use for and typically is this dot notation. For or, we use a plus sign, and for not, we use an overbar. You will see some other notations as well, so don't get confused if sometimes you see something else in the literature, but in general, these are the ones we're going to be using. Okay, and so in this particular example, the way that I would specify what it is that this function does is using this Boolean expression. And so what is this telling me? This is telling me if C is not true, then I'm going to pass along A, which is this first term. And then if C is true, I'm going to pass along B. Okay, and we're going to get into many more examples of this as we continue in today's lecture. All right? And so the key here is that for any combinational function, we can use either truth tables or these Boolean expressions to specify exactly what the circuit needs to do. Okay, so now let's take a little bit of a closer look at Boolean algebra and exactly what it means to have variables that can only take on one of 2 values, 0 and 1. And so we talked about 3 basic operations, and, or, and not. And through these truth tables right here, we're expressing what exactly these operations mean. And so probably just as you would expect, the AND gate, what it does is the only time it'll produce a 1 output is if both the inputs A and B are both set to 1. Okay? On the other hand, the OR gate, which is this one right here, will produce a 1 as long as one of the inputs is a 1. So the only time it doesn't produce a 1 is when both A and B are 0. And finally, the NOT operation, which is over here, takes any input 0, flips it to a 1, and a 1 to a 0. Okay? Now, with these basic operations, we can actually produce any circuit that we want. Okay, and so we're going to go into a lot more properties and details and even different gates, but you could actually live with just these 3 gates alone as far as functionality is concerned. All right, so instead of using truth tables to define these 3 gates, we can also define them using the following 3 axioms, which is the basis of all of Boolean algebra. So the axioms look as follows. The first one is the identity, which says that any variable ANDed with a constant 1, you're always going to get back that variable. Okay? Similarly, any variable ORed with a constant 0, always going to return that original variable. Okay? The next identity is the null identity, which says that if I AND something with a 0, it's always going to return 0 regardless of what my variable was. If I OR something with a 1, it's always going to return a 1. And finally, the negation is as we saw before, okay? And so one thing that's very nice about Boolean algebra is this principle of duality. The principle of duality says that if I have a valid Boolean expression, then if I replace all my 0s with 1s and 1s with 0s, and similarly I replace all ANDs with ORs and ORs with ANDs, then I will end up with another valid Boolean expression. Okay, so if I look, for example, at my first row here, the identity, if I replace this 1 with a 0 and the AND with an OR, I basically get my other identity. Okay, so the nice thing about this is, you know, we only have to remember half as many expressions. Okay? All right, now in addition to these yes? It means that it's true. So if it is true that, you know, A ANDed with 1 returns A, it's also going to be true that A ORed with 0 returns A. Okay, so it results in another valid Boolean expression. Okay, so there are a number of algebraic properties that we use in order to manipulate our Boolean expressions, and I'll let you guys look on your own at most of the details of these. Most of them are should be pretty familiar to you from integer algebra, but I want to point out just a couple. Specifically, the reduction property. So the reduction property as well as the absorption properties are properties that we use a lot in order to simplify more complicated Boolean expressions into smaller Boolean expressions. And you're actually going to get practice doing some of that, and you'll see how it's important in order to end up with more optimized circuits. We're going to want to try to minimize our Boolean expressions, and this is going to be, these are going to be 2 properties that we use heavily in order to do that. And the last property that I wanted to point out is DeMorgans Law, which often tricks people up because it's not necessarily so obvious. And so the key here is to notice where the overbar is here. Okay, so if we have A and B with an overbar over the entire thing, that is not equal to A bar and B bar. In fact, it is equal to A bar or B bar. Okay, and we'll go through a proof of that in just a second. But the key is that you really want to be careful about these overbars and whether they're covering an entire statement or just a single variable. Okay, so a lot of these properties are easier to remember because they are similar to your integer algebra, but you do want to just keep in mind that some of these actually are different. So in fact, if you look at the distributive property for OR, in Boolean algebra it holds true, whereas in integer algebra it doesn't. So while there is a lot of analogy, there are some differences to keep in mind. And then in general, in order to familiarize yourself with these properties, we don't want you to just go ahead and memorize them. Instead, we want you to derive them. So let's go ahead and derive DeMorgans Law in order to convince ourselves that DeMorgans Law is in fact a valid property. Okay, and so what we're saying here is that given my inputs A and B, which can take on the following input combinations, right? I can either have A and B, the whole thing negated, right? And so A and B, we said, produces a 1 only when both of my inputs are 1. So A and B bar is going to produce a 0 only when both of my inputs are 1. And similarly, it'll produce a 1 in these cases. All right? Now, what about the expression A bar or B bar? What is that going to give me when both of my inputs are 0? 1. How about the next one? 1, right? So as long as one of my inputs is 0, I get a 1, and in the last case, I get a 0. And so sure enough, DeMorgans Law is in fact valid. Okay, and so you can do the same thing for all of the other properties if it's not immediately obvious to you why they hold. Okay? Any questions about that? Sorry? Oh, yes. No. So if there is ever something that matters, it would be expressed with parentheses, but you'll see that that doesn't apply here. Okay, so given our truth table, or the Boolean expression that goes with a truth table, what we can do is we can basically represent, sorry, let me take a step back. Let's assume I have this truth table here. In order to go from this truth table to a Boolean expression representation of this truth table, the way that we want to do this is I want to look for all the rows that have a 1 in them, and write down a product term that corresponds to that row. And so in this particular example, it's going to look something like this, the Boolean expression for this truth table. So how did we derive this? Well, let's take a look at the first one in our truth table. The first one corresponds to the row where C is 0, B is 0, and A is 1. Okay? The way that we express that as a product term is C bar, B bar, A. And so when that holds true, then our equation for y is going to return a 1, which corresponds to the output that we're expecting for this function. Okay? Similarly, for all of the other ones, we're also going to produce these product terms. And together, this is going to create what we call the normal form. What's nice about the normal form is that it's a unique representation using Boolean algebra of what it is that your function does. However, there are simpler ways of expressing the same functions, which we'll get to in a little bit. Okay, so we can use Boolean expressions as well as truth tables to express the functionality of any circuit. Now, what we want to do is we want to move on, and we want to take this these Boolean expressions and figure out how to turn them into combinational circuits. Okay? So the way that we're going to do this is what we want to do is we want to create something that's called a logic diagram, where we take our basic gates, the and, or, and not gates, and we combine them using wires in order to produce a circuit that implements the basic function that we're trying to implement. So as we mentioned before, we have 3 gates, or 3 basic properties, which are and, or, and not. So you want to become very familiar with these particular circuit representations of these gates. So you'll see the AND gate has a flat back. The OR gate has this curved back. And then an inverter, if you recall from last time, this triangle was our representation of a buffer, which says just takes an input and produces the same output. If we put a little circle on the output, then that turns it into an inverter, meaning that we take whatever's on the input and we flip it to produce the output. Okay, so these are our 3 basic gates. You're going to see them over and over and over again. Another thing that you want to note is that so far we've just been talking about 2 input gates, but it's possible sometimes to want to take the AND of more than just 2 variables. So for example, in this case, we're showing a 4 input AND. And so you do have gates that allow for more than just 2 inputs, we don't go, crazy about it, because at some point it becomes not really realistic or useful to build a 16 wide AND gate, and so instead we would build it out of some smaller gates that we have available. The last thing to mention about these 3 gates is that they're what we call universal. So what it means to be universal is that I can build every single possible Boolean combinational circuit using just ands, ors, and nots. So let's take a look at how we can do that. So here's a straightforward way to go from a Boolean expression to a logic circuit. All right, what we're going to do is we're going to take our normal form representation of our function, which is what we see up here. And here we have one product term corresponding to every one in our truth table. And basically what you're going to do is for every input that has a bar over it, you're going to have an inverter. For every one of these product terms, you're going to have a corresponding AND gate. And then at the end, you're going to have a 4-input OR that takes these 4 product terms. So each one of these product terms corresponds to one of these terms in our Boolean expression. So this one, for example, is C bar, B bar, A. Okay? And you have the same thing for all of the other ones. So as you can see, we can very easily build a circuit that can do absolutely any function. However, it turns out that in many cases, we can build a circuit that's going to implement the same function, but with fewer gates. And so that's what we're going to talk about next. So far, we've talked about our normal form representation of our Boolean equations. Another way that we refer to these is as a sum of products, okay? And the reason we call it that is because we're basically, at least if you think about it from a math term, you have terms like, here's a product term, ORed with, another product term. And so this refers to the sum. This is what we call a product. And so the sum of products is what we call this representation. Now, a couple things to note about this. In sum of products representation, you will only ever have an inversion over a single variable, okay? So you'd never see something like this in a sum of products representation, okay? Now, given a sum of products representation, we want to figure out, well, what's the minimal sum of products representation for a given function so that we can implement it with fewer gates. And so what it means to be a minimal sum of products is that we're using fewer AND and OR gates than what the normal form does. The one caveat, though, about minimal sum of products is that it's, unlike the normal form, it's not unique. Okay, so it's advantageous in the sense that it can be built with fewer gates. It can, as a result, probably be faster and smaller, but there can be more than one solution that implements the exact same function. All right, so if you have a small number of variables, like 3 or 4, you can take the properties that we saw at the beginning of lecture and use them to manipulate your normal form Boolean expression in order to simplify it by yourself. So for example, let's take this equation that we've seen a number of times now. And if you recall, we talked about the reduction property. So if I look at these 2 terms highlighted in blue, you'll notice that there is a common term, CB, in both of them. Okay, so I have CB ANDed with A bar, ORed with CB ANDed with A. And from the reduction property, we know that that's equivalent to just CB. Okay, so I can take this expression that consists of 4 product terms and turn it into 3 products. Now I can apply reduction once again on the outer 2 terms, and I can end up with a much smaller term that expression that represents the exact same function. And if you think about what I'm going to need to implement this function, I now have a single inverter, a 2 ANDs, and 1 2-input OR, whereas my original expression had a whole bunch of inverters, 4 3-input AND gates and a 4-input OR, which was much more complex, even though they implement the exact same functionality. Now, beyond 3 or 4 variables, it starts to get unrealistic to do this by hand, and so we actually use tools to do this. Before we move on to talk about the tools, I want to just point out a couple other methodologies that are used in order to help us with the Boolean simplification. So one of them is using truth tables with don't cares. The X's here are what we call don't cares, meaning that if I have a variable b right here that's labeled as an X, it can either be a 0 or a 1, and the row will produce the same output. Okay? And so if I look, for example, at the second row here, which corresponds from the original truth table to both the rows of 0, 0, 1 as well as 0, 1, 1, they both produce a 1, and this corresponds very clearly to the term C bar A because B doesn't matter. Okay, so that's another way of identifying that reduction property and simplifying your normal form to a simpler Boolean expression. And the last way that you can simplify Boolean expressions that we want to mention here, although there are others, is multi-level Boolean simplification. And the idea here is, suppose that I have, this 4-term sum of products, and this sum of products is actually a minimal sum of products representation. So if I took it directly as a minimal sum of products and implemented it, I would have 4 AND gates and an OR gate at the end of it, so for a total of 5 gates. However, if I do some manipulation of this logic, I can notice that the A or B term is shared. And so I could create a new variable, temporary variable, call it X, which is A or B, and then my function is equal to XC or XD, which, if I draw it out, simply consists of 2 OR gates and 2 AND gates, which is fewer than the immediate representation of the original minimal sum of products. So this is just, to give you a sense that there are lots of different ways of implementing these circuits. We don't expect you to be able to identify them all. In fact, this is why we use tools, is exactly because there are so many different ways that you want to consider that it becomes infeasible to just do this by hand. Okay, so what we're going to do is we're going to use a synthesis tool instead of trying to do this by hand. And what we want to do is we're going to give the synthesis tool several pieces of information. The first is a high-level circuit description. So it's either going to be a Boolean expression, or in our case, we're going to use the blue spec high-level description language to specify what it is that we want our circuit to do. Then our second input is going to be a standard cell library, which is going to say which gates are available to us. So do we have, a 2, 3, and 4 input AND gate, or do I have an 8 input AND gate available to me? As well as what are the characteristics of delay and power and area for each of those gates. So that goes to the question that you had earlier. And finally, the last piece of input that it's going to take is what am I actually trying to optimize for? So depending on what my goal is, am I trying to optimize for a minimum delay or the smallest area or a minimum power, I'm going to come up with different circuits for these for the same functional representation. Okay, so moving on. I just want to quickly introduce a couple other gates beyond the AND, OR, and NOT, which you're going to see a lot in this class. So the first is an exclusive OR. You'll notice that the representation for it is just like the OR, except that it has this one extra curly input. Okay? And the definition of an exclusive OR is shown here in the truth table. It says that you only get a 1 on your output when exactly one of your inputs is a 1. So only if A or B is a 1, but not if both of them are a 1. So the Boolean expression for that is to say A bar B or A B bar, meaning I can only have exactly one of them be a 1 while the other is a 0. Notice that we do have exclusive OR gates with more than 2 inputs, and in that case, the expectation is that you get a 1 if you have an odd number of 1s. The other 2 types of gates that I want to point out are a type of gates which we call inverting logic. And typically, we're going to actually want to use inverting logic because in the technology that we use today, inverting logic has a lot of advantages in regards to delay and size. And so the gates that we use a lot are actually NANDs and NOR gates. So a NAND is basically an AND gate with an inverter after it, and a NOR gate is an OR with an inverter after it. And the cool thing about NANDs and NORs is that just like we said, we can implement any Boolean expression using the three gates and, OR, and NOT. It actually turns out that NAND and NOR gates themselves are universal, meaning you can build anything out of just this one single type of gate. Okay? And what this is showing you here is how from a NAND gate I can build an inverter, I can build an AND gate, and I can build an OR gate. Sorry, similarly, I can do the same thing with just NOR gates, okay? And so the point of the slide here is just to show you that these gates in themselves can actually be used to implement any logic expression. It's sometimes a little bit hard to see it, but this is equivalent to an AND gate, and this is equivalent, to an OR gate. Okay, so what we want to do now is talk about some of these properties of our different gates. And so in addition to doing simplification on our Boolean algebra so that we can make the functional specification just be simpler in terms of ANDs and OR terms, we also want to think about what are the properties of the gates that are available to us. So here we have an example of some basic gates and their properties. Specifically, we're looking at delay and area. And a couple of things that I want to point out are the following. So if we look at just the inverter and the buffer, you see that the negating logic, the inverter, is much smaller and faster than the buffer. Similarly, if we look at our two input gates, our negating logic, the NAND and the NOR, are also smaller and faster than the AND and OR. And same thing holds true for our four input gates. The other thing to notice here is that in the four input gates, our delay and our size is larger than in the two input gates. So a few observations basically to take home from this slide are, number one, because of the way that we implement our gates, which is that we use CMOS, which stands for complementary metal oxide semiconductors. It's the way that it works is through complementary logic. It turns out that, and you don't need to know the details of how we actually build these gates, just to know that complementary inverting logic is typically faster and smaller than non-inverting logic, okay? And so it's often the case that we'll want to use NAND and NOR gates instead of AND and OR gates, okay? The other thing to know is that as the gates become larger and larger in the number of inputs that they have, the delay becomes larger and larger. And so this is why we don't want to have necessarily an 8-input AND gate or a 16-input AND gate, because at some point it affects the speed and the area too much to be useful. Okay, so given that we have these, delay and size trade-offs, for something as simple as a 4-input AND gate, I might have to, decide, do I want to use a 4-input AND gate directly? Or do I want to use a 4-input NAND gate followed by an inverter? Or do I want to use this more complicated thing here shown at the bottom of the slide, which is also equivalent logically to a 4-input NAND gate using DeMorgans laws? So if I take a look at the delays and the area costs of these three different implementations of a 4-input AND gate, I see that, in the first two, I have 90 picoseconds and 40 microns squared for area, whereas in my second one, which looks a lot more complicated, while the area goes up a little bit, my delay is actually significantly less. Okay? And so whenever we are taking our Boolean expressions and turning them into logic circuits, we really want to be thinking about what is it that we're trying to optimize for. Am I trying to minimize area, or am I trying to minimize delay for my particular circuit? All right, here's another example. Suppose that I have this combinational circuit, which consists of a bunch of NANDs and inverters. And I have a target library that consists of these 4 gates. The inverter, a 2-input NAND, a 3-input NAND, and a 4-input NAND. And each one has an area associated with it. Suppose that I was trying to now optimize for minimum area rather than minimum delay. Well, I have a number of choices of how to cover all of these gates. So here's 2 examples of how I might cover these gates using the target library that I have. I can either cover each of the NAND gates individually, and which will end up with a total of 7 NAND gates and 5 inverters for a sum of 31, which is my cost for my area. Or instead, I might realize, like over in this circuit on the right here, that the combination of these 3 gates corresponds to a 3-input NAND gate, and the combination of these 5 gates corresponds to a 4-input NAND gate. And so now my cost, as far as area is concerned, has gone down from 31 to 19. Okay? So these are the types of things that our optimization tools are going to be doing for us. Because they're receiving, one of the inputs they receive is the target library, it's going to actually try to figure out what is the best implementation for your circuit given what you're actually trying to minimize. Okay, so couple takeaways is basically we've seen a number of ways of turning optimized circuits into turning Boolean expressions into circuits. And you see that there's a lot of complication involved in terms of doing, Boolean simplification, mapping to the correct target library, worrying about what your ultimate cost function is. Is it delay, area, power, some combination of the two? So because of all of that, it's really infeasible to do this by hand. And in fact, what we're going to be doing in this class is we're going to be using a hardware description language called BlueSpec in order to describe all of our circuits. And we're going to use automated synthesis tools to produce the optimized implementations of these circuits. Okay, so to summarize, we saw that and, or, and not in themselves are a set of universal gates. I can build every single Boolean expression out of just ands, or, and nots. Similarly, I could also build things out of only NAND gates or only NOR gates. In addition, we saw that I can take any sum of products representation in the normal form, which would be representing every single one in my truth table via a product term. I can then turn that very easily into a circuit by using an inverter for every single overbar, using an AND gate for every product term, and using an OR gate for ORing those product terms together. And finally, as we've said a few times, there's a lot of trade-offs in mapping Boolean algebra or Boolean expressions to circuits, and we want to be able to consider all of those. So just to finish up for today, this is the take-home problem for today. You have the following Boolean expression. You have it also in the back of your handout. So what you want to do with that is produce a minimal sum of products, and also you want to map it to gates in order to minimize the area. All right, thanks everybody. We'll see you next time.